Okay, assalamu alaikum students. Are you able to hear me? Okay, so let's start with today's lecture. Today we are going to start chapter number 15. So this is going to be the last chapter in terms of studying the dynamics of particles. Then after that we are going to, well, actually our dynamics is over for particle, and then we are going to do the dynamics for the rigid bodies. The laws for the dynamics of the particles and for the case of rigid bodies are same, except only there is an additional factor of rotation which will be there then added into it in the study of the dynamics of the rigid bodies. Anyways, for now, this chapter is about the kinetics for the particles, and here we are going to study the kinetics using the principle of linear impulse and momentum. So this is about this topic. So you know that Newton's second law says summation F is equals to ma. Okay. So it says summation F is equals to ma, but acceleration can be written as dv by dt. So we get summation F is equals to m dv by dt. Okay, now what we can do is that we can put dt on the other side. So it becomes summation F dt equals to m dv. We can then integrate it from at time t1 to t2 and v1 to v2. So this becomes mv2 minus mv1, and this whole term is as it is. Force applied at a very for a time from t1 to t2, and this thing is known as impact. This thing is known as impact, or sometimes we call it I. So the I is equals to mv2 minus mv1. So this becomes our main formula for principle of impulse and momentum. Mass is the mass, v is the velocity, v1 is the initial velocity, v2 is the final velocity, and this is the impulse. Okay, this is the impact. So it's summation integral t1 to t2 f dt. Is this formula clear to everybody or not? Is there anything which is not clear in this formula?
Yes, it's clear.
Okay. So this summation f dt t1 to t2, this thing is known as impulse. This is the formula for linear impulse and momentum. We are putting the word linear here because there is going to be an angular impulse and momentum in the same chapter we are going to study later. But for now, this is linear impulse. Okay, this I is the impulse, and it is f t dt integral t1 to t2. If f is constant, then f will come out of the integral and it will become I equals to fc into t2 minus t1. So this is the formula for principle of linear impulse and momentum. mv1 plus summation integral f t1 to t2 dt equals to mv2. Now, since velocity here and the force are both vector quantities, so we can write it in terms of the Cartesian coordinates. So we can have mvx1 equals to summation fx dt equals to mvx2. Similarly, in the y coordinate system, we can write. Similarly, in the z coordinate system, we can write. So that one equation could be split into three equations based upon if you want to do it in the Cartesian coordinate systems. Okay, you need to understand the formula here, and you need to understand what is happening. Let's say that I have an object. This is an object, okay? And the mass of the object is m. And let's say this object is initially moving at velocity v1, okay? So let's define the boundary of the object. This is the boundary, dotted boundary, okay? So what happened is that suddenly an impact is made over the object. When we say the impact is made, we consider the impact which is made on the boundary. Okay, if something is happening inside, we are not concerned with it. But if an impact is made over the boundary, so now this this impact is going to change the velocity of the object. Okay, so if we had mv1, then an impact is made. So a force is applied for a specific time from t1 to t2. And so this is the impact which is made over, but this impact should be made over the boundary. Okay, I'm using the word boundary here again and again because it has a significance, and you're going to see that when we're going to start solving the numericals, then you're going to see what is the significance of the boundary. Okay, so I say here that, okay, this is the object, mass m, velocity v1, and it has a boundary. Okay, over the boundary an impact is occurring, and when an impact occurs over the boundary, so this impact causes change in the velocity of this object. The mass doesn't change, mass remains the same, so it becomes so now the momentum becomes mv2. So this is what is happening here. Okay, is this clear so far?
Yes, clear.
Okay. Okay, so let's see the problem. We have a 0.5 kg ball that strikes a rough ground and rebounds with the velocities shown. Okay, neglect the ball's weight during the time it impacts the ground. Find the magnitude of the impulsive force exerted on the ball. So obviously the ball was had a mass. Okay, so the ball had a mass, and this ball was moving with a velocity 25 meters per second. It strikes the ground, obviously because of the striking, and impact is now applied over the ball. Okay, and so the ball is instead of moving, so it rebounds and rebounds, and when it rebounds, its velocity is now changed from 25 to 10 meters per second. Okay, obviously the mass of the ball remains the same. Now we need to find out the magnitude of the impulsive force. How much is the impulsive force? What is the magnitude of the impulsive force which is being applied? So we see here that the ball is changing direction. Okay, so initially it was moving at a certain angle, and then it started moving at a different angle. Okay, so we have two ways of solving the problem. One way is that we solve for the x component, we solve for the y component, then we can add them together to get the overall magnitude of the impulsive force. The other way is that we solve it in the vector format, and it's in one step. So the first thing is that we need to draw the free body diagram. Now for the free body diagram in chapter number 15, it's basically a big free body diagram. Why? Because you have to mention everything. The first thing is that the ball was moving at 45-degree angle, and that was the momentum mv1. Then plus this thing happened, okay? And this thing, even if you don't draw this, if you don't write this, it's okay. But actually what happened is that an impulsive force acted over the object. Okay, this happened when the strike occurred on the ground. And then the final result is that now the moving ball is moving with mv2 at angle 30 degrees. So this is the complete free body diagram, and you have to draw all the three things into it in the same way as it is drawn here. First, what was the situation, then plus sign, then impact equals to, then like this. So in the same way you have to draw in the exam if the problem you are solving for chapter number 15. Okay, so we have this, the free body diagram we made. Now we can write down the equation. The equation is mv1 equals to summation f dt t1 to t2 equals to mv2. Okay, now mv1 mass is same, velocity we can put the velocity into the vector format into I and j components. Okay, so if you look here, it was 45-degree downward, so it will have x component in the positive direction and y component negative. So 25 cos 45 I minus 25 sine 45 j. Okay, so that will be the vector format, and plus summation f dt t1 to t2 equals to mv2. Okay, then when it is moving 30 degree in the upward direction, so x component positive, y also positive. Once we have this thing, we can find what is the impulsive force vector. Okay, just add the I components together, or summation or subtraction of the I components and the j components, so you get this thing. Once you have this thing, you have I component and j component resultant. You can just take out them to find out the magnitude. So I component is square plus j component square under root is going to give you the magnitude. Before moving forward, is all these steps are clear or not? Is there anything which is not clear to anybody? Okay, let's move ahead. So example 1 done. Let's move towards example 2. So in example 2, what happened is that we have a 100 kg stone, which is shown in the figure, is originally at rest on the smooth horizontal surface. So we have this originally at rest on the smooth horizontal surface. If the towing force of 200 Newton acting at an angle of 45 degrees applied to the stone for 10 seconds. So 200 Newton force is applied for 10 seconds. Determine the final velocity and the normal force which the surface exerts on the stone during this time interval. Okay, so we can again solve this problem using chapter number 15 methodology. Okay, so if we use it using the principle and impulse methodology, you have to draw the impulse momentum diagram. Okay, so impulse momentum diagram will be what? Initially it was at rest, then plus, okay, you don't need to draw this, okay, normal and the weight component, but yes, there is a force applied, and this force applied for 10 seconds at an angle of 45 degree. Okay, and so the result is equals to that this stone is now moving in the x direction, mv2. Okay, so this is the diagram. So now this again, this problem could be solved in the same way as we did before. We did it in the vector format before. Now we are doing it by splitting it into x and y components. So if we do it by doing it into x and y components, then it will be mvx1 plus summation t1 to t2 integral fx dt equals to mvx2. Initially the velocity was 0. Okay, and the final velocity we need to find. Okay, mass is known. Okay, this thing, because the force is constant. Okay, the force is constant, 200 Newton. So it will be 200 into cos 45 for 10 seconds, t1 to t2. So it will be 10 seconds. So you just substitute the values, you'll get what is the velocity v2. And then since it is also required to find out the normal force which is exerted, so we can apply the same equation in the y direction. So vy1 was 0, vy2 is also 0, okay, because there is no motion in the y direction. So we have just this thing. So summation of forces in the y direction is 0. This is what it is. Uh, okay, so summation of forces in the y direction will be what? It will be nc minus the weight plus component of the force in the y direction. That thing equals to 0, so it's going to give you nc. Okay, one student is asking why F cos 45. You see here the force. Um, we have to understand here we are writing it in the x coordinate and y coordinate. So when we are talking about Fx, the force was not acting in the x direction. But if we want to find Fx, so Fx would be 200 cos 45. Do you get it? Okay. So that's the solution of this problem. Actually, the solution is done. So is there anything within the solution which anybody do not understand? Please ask. Okay. Okay, let's have another problem. The 12 megagram jump jet is capable of taking off vertically from the deck of a ship. If its jet exerts a constant vertical force of 150 kilonewton on the plane, determine its velocity and how high it goes in t equals to 6 seconds starting from rest. Neglect the loss of fuel during the lift. Okay, so this is a jump jet. Jump jet means it's a kind of an aeroplane which do not need the tires to go over the runway and then fly. So there is a jet which is coming out from bottom, and that jet is going to push the plane to go up. So in order to solve the problem, since the motion of the plane is only in the upward direction, so we only need to apply the impulse and momentum law in the y direction. So it will be mvy1 equals to summation fy dt equals to mvy2. So initially it was at rest. So initially the velocity is 0. Okay. And now we need to find at what is the velocity now. Okay. So it was starting from rest, but after 6 seconds, we want to know what is the velocity. So this is what we want to find out. Mass of the jet is given. So it is known. Okay. And the force is constant. Constant is mentioned. It's a constant vertical force of 150 kilonewton. So it's 150 kilonewton. Now, in the vertical direction, there are two things that will be acting. One is the force of this jet, which will be pushing it to move up, and then the weight of the jet will be pushing it to move down. Okay, so it will be 150 kilonewton multiplied by dt. So time is 6 seconds minus weight. So weight is 12 megagram. So mg into dt. So with this, if you solve it, you're going to find what is V2. And if you know what is the velocity, then we also need to know how high it can go. Then how high it can go, we can solve the problem using the laws of chapter number 12. Is it clear so far? Is there anything within the solution of this problem which is not clear? Please ask. Is the solution clear? Feel free to ask any question if you feel any difficulty at any point, okay? Okay, so okay, let's see this problem. The 28 megagram bulldozer is originally at rest. Determine its speed when t equals to 4 seconds. If the horizontal traction force varies with time. This time the force is not constant. It's varying with time as shown in the figure. It's not constant, but it's mentioned that f is a function of time. It's 4 minus 0.01 t squared. Excuse me. Okay, so f is equals to 4 minus 0.01 t squared. So force as a function of time is provided. So the only thing that we need to do is we need to just substitute this into the main equation. So it started from rest, originally at rest. So vx1 was 0, okay, and final velocity we need to find. The mass is provided. So we have to put summation integral t1 to t2 fx dt. Okay, so f as a function of time is provided. So it's 4 minus 0.01 t square. This was given in kilonewton. That's why 10 to the power 3 is added here. Okay, then we have to integrate it dt from 0 to 4. So now it's just a matter of integrating it yourself, get what is the velocity. Is the solution clear? Is there anything within the solution which is not clear? Please ask. Okay. Okay, so let's discuss about the principle of linear impulse and momentum and conservation of linear momentum. Okay, what does the conservation of linear momentum says? If you have a system of bodies, if you have more than one bodies, then whatever the linear momentum you have initially will be the same as the linear momentum that you're going to have finally. Okay. Okay, so let's directly come over to a numerical and start solving it. This will be the best way to understand the concept. Okay, so we have an object M and its mass was 100 kg and its velocity was 20 j. So it was moving in the j direction with 20 meter per second. Okay, what happened was that this mass was split into three parts. So it just exploded into three parts. An explosion has broken the mass m into three smaller pieces, A, B, and C. So for A, it has a mass of 20 kg, B has a mass of 30 kg, C mass is not given. And A velocity is now 50I, 50J, B velocity is minus 30I, minus 30K, okay? And we need to find what is the velocity of C after the explosion. So the thing is that initial momentum, there's a conservation of momentum. What was the initial momentum? Which will be the same as the final momentum. So initial momentum was m into v for this object. Now final momentum will be mv for A, then we will have mv for B, then we'll have mv for C. But this A, B, and C came out from this main object. When this exploded, it became this thing. So if you add the momentum of all the three, it should be equal to the momentum of this main. You get the idea? Momentum is conserved. Whatever the initial total momentum, it should be the same as the final total momentums. Okay, so for the mass, we can find out because the total mass was 100 kg. So mass A is 20, mass B is 30. So the remaining mass C should be 50. So the mass is conserved. So it's mv equals to mava plus mbvb plus mcvc. So we just need to write. So we know m, we know v for this, we know ma, we know va, we know mb, we know vb, we know mc. vc we don't know, so let's write vc as vcxi, vcyj, vczk. So if we solve for the I, J, and K components separately, we're going to get the values of VCX, VCY, VCZ. And if we know VCX, VCY, VCZ, we can find out what is, if we want to find, we can find out the magnitude of VC as well. So solution of the problem is done. Is there anything within the solution of this problem that you do not understand? Please ask. Actually, it's not difficult. Okay, so these 2-3 problems are going to take time a little. Okay, so let's have a break of 5 minutes and then we're going to start back again. Okay, somebody has asked, is the moment have direction? Yes, the moment have direction because moment is mass into velocity. Mass is a scalar quantity, but velocity has a direction, so the moment has also direction. Okay, so let's have a break of 5 minutes and then we're going to start back again. Okay, assalamu alaikum. Okay, one student is asking in example 2. In example 2, why we assume that there is no motion in y direction? In reality, there is no motion in y direction. It's a big stone, heavy stone, and moving in the x direction. Okay, so just look at the problem and you will see that its motion is only in the x direction. Okay, let's see this problem. 2 rail cars with masses ma 20 megagram and mb 15 megagram and velocities as shown. They are coming towards each other. Then we need to find the speed of car A after collision if the cars collide and rebound such that B moves to the right with a speed of 2 meters per second. Also find the average impulsive force between the cars if the collision takes place in 0.5 seconds. Okay, now let's look at the solution of this problem. First of all, here we have 2 rail cars. Okay, the mass of the rail cars is provided. So we know what is MA mass, and mass B is 15 megagram. Okay. Then initially the rail A is moving at 3 meter per second and B is moving at 1.5 meter per second. Okay. Then later on what will happen, the two will come close to each other and they will actually collide. After collision, what will happen? B will move in this direction. Okay, so it says that it rebounds such that B moves to the right. B moves to the right with a speed of 2 meters per second. So after collision, it is moving with speed of 2 meter per second. We need to find what is the speed of car A after collision. Okay. Now, in order to solve this problem, what we are going to do is that initially we will take our boundary as this. So we take the whole two cars together as our boundary. Now, when we say this, so now there is no impact over the boundary. There is no impact over the boundary. Just the momentum is conserved. Just the momentum is conserved. So no such impact on the boundary. Okay. So since the momentum is conserved, so we will have M A V A plus M B V B, and this thing equals to M A V A plus M B V B. This was for initial, and then you'll have the same for the final. Okay. So by this way, we can actually solve the first part of the problem. So let's see this. So it's MAVA1 plus MBVB1 equals to MAVA2 plus MBVB2. Okay. So the masses MA, MB, MA, MB known. Initial velocity VA1 is known. VB1 is negative 1.5. You see, because VB is moving in this direction. So it's negative 1.5. We need to find what is the final velocity VA2. Okay, but we know what is the final velocity VB2. Finally, it will move in the right to the right at 2 meters per second. So if you solve it, you will find what is VA2. This is how we are going to solve the first part of the problem. Before moving forward, is there anything within the solution which is not clear? Please ask. Is the solution clear so far? Okay, now we need to know that how much is the impulsive force. How much is the impulsive force? Now, if we want to find how much is the impulsive force, now we need to change our boundary. Okay, so let's say that we put one of the rail, let's say this rail A, we put the boundary as our rail A. So for rail A, we have an initial velocity. Then once the impact is done, then we will have the final velocity of rail A, and we can find out what is the force of impact. This force of impact was not there in this formula. Why? Because here we consider our boundary as the complete thing. So on the boundary, there was no impact. But here, if we put only rail A as our boundary, then for rail A, it's MAVA1 plus summation FDT equals to MAVA2. Now we can find out the force of impact. Before moving forward, do you understand this point or not? Is this point clear?
Doctor?
Yes.
If I take B, is it okay?
It's okay, because both forces will be same. If you take B, no problem. Okay, let me again repeat it. Okay, the first thing was that we needed to find what is the velocity of VA after collision. So what we did, we took the boundary as the entire two rails together. So no impact was there on the boundary. The impact is happening inside, but inside we don't care. Inside is not this thing. Inside is not this thing. It should be on the boundary. Okay, so impact was happening inside, but inside we don't care. We do not need to write FDT because it's always on the boundary. So what's happening inside is that the momentum is conserved. Whatever the momentum was there before, collision is the same momentum after collision. So from this we find what is VA2. Okay, now we need to find what was the actual impact over A and B. So if we want to find out the impact force, so now we need to change our boundary. Instead of putting the boundary as the complete thing, now we put the boundary over A only. Okay, so this is our boundary. Okay, so now when the A is going to collide with B, so the impact is occurring over the boundary. Okay, so we have MAVA1 equals to integral F dt equals to MAVA2. We know what is VA1, we know what is VA2, we know what is mass of A. We can find out what is the force of impact. So this is the force of impact. If the average force was given, if we need to find the average force if the impact occurred in 0.5 second, so we can find what is the average force. This is how we solve the problem. Do you understand the solution or not yet? Is there anything in the solution that you don't understand? Please ask. Okay. Okay, this is the next problem. So we have, okay, once again, some student is asking why it become negative. Okay, let me go back. Oh, okay. You're asking this, that why it become negative from positive to negative here? Is this you're asking? Uh, in the end, let's say you keep it positive. Let's say you keep it positive, you get the answer negative. Negative doesn't mean anything here. Okay, because they wanted to keep the answer in positive. That's why they, instead of putting a positive here, they put a negative here. Okay, so there is no specific reason. We just needed to find what is the average force. Okay, irrespective of the direction here. Okay, so let's see this problem. Okay, 800 kg rigid pile shown in the figure is driven into ground using a 300 kg hammer. The hammer falls from rest at a height of 0.5 meter and strikes the top of the pile. Determine the impulse which the pile exerts on the hammer if the pile is surrounded entirely by loose sand so that after striking the hammer does not rebound off the pile. This is a comparatively difficult question. Difficult question not in terms of the solution, but in terms of understanding the problem statement itself. Okay, so we are going to spend some time first understanding the problem statement. Solution, we're going to go for it later. But first, let's understand the problem statement. So what's the problem? The problem is that we have a pile. This is a pile. Okay, and we need to put the pile in the ground. So the idea is that we have a very huge hammer, and what we do is that we pull the hammer up and then we release it. So the hammer will come under the effect of gravity and hit the pile. Once it hit the pile, it will push the pile a little down. Okay, then we raise the hammer again, then we release it, then it's going to hit the pile, and so slowly we are pushing the pile into the ground. Okay, so this is what is happening. Okay, before moving further forward, do you understand what is happening here? Okay, now let's see the problem statement. What does the problem statement says? The 800 kg rigid pile. So the pile is 800 kg. So we know what is the mass of the pile. This is mass of the as shown in the figure is driven into the ground using 300 kg hammer. So this hammer is 300 kg. So we have the mass of the hammer as well. Okay. The hammer falls from rest at a height of 0.5 meters. So every time what we do is that when we raise it, when we raise the hammer, how much we raise the hammer? 0.5 meter. So 0.5 meter, we raise the hammer up. The hammer is initially at rest, then we release it from rest, and the hammer falls on the pile and push the pile down. Okay, so this is 0.5 meter. Yes, it is constant. So every time we raise it 0.5 meter up, then it's like you have a hand, and with your hand you are pulling something up and then releasing it. So it's going to go with its weight down, hit it, then you go down, catch it again, bring it up, release. So it's a continuous process going on. Okay, so so the hammer falls from rest at a height of 0.5 meter and it strikes the top of the pile. Obviously, it strikes the top of the pile. This is the top of the pile. Determine the impulse which the pile exerts on the hammer if the pile is surrounded entirely by loose sand, so that after striking, the hammer does not rebound off the pile. Now, this is an interesting statement. Please focus on this statement. Okay. What does it say is that the sand here is loose. You know what happened in the loose sand? When the hammer is going to strike the pile, after that, if the sand was not loose, the hammer would rebound, would go back. But here what we're saying is that since the sand is loose, so after striking the pile, the hammer and pile together move as one body downward. So they move both with the same velocity. The hammer does not get separated after striking. So determine the impulse force which the pile exerts on the hammer if the pile is surrounded entirely by loose sand, and so that after striking the hammer does not rebound. So the hammer does not rebound. Hammer gets attached with the pile and move together with the pile with the same velocity of the pile after striking. Okay, so this is what is said. So do you understand this statement? This statement here is basically the code here, which is going to give you some information. So the information that you get. Okay, one student is asking, so there is not a force from pile to hammer. Actually, the hammer is pushing the force over the pile, uh, is applying the force over the pile, but the pile will have a reactive force, right? So pile will have a reactive force over the hammer. So there is no force. Okay, so did I answer your question? So we are talking about the reactive force of the pile on the hammer. Okay, so it will be the force of impact. It will be the impulse that we are talking about. But the thing is that after collision, the hammer does not get separated, but hammer moves with the pile with the same speed of the pile. So the velocity of the hammer after collision is the same as the velocity of the pile. VH, let's say call it VH2, is equals to V pile 2. After collision, that do not get rebound and it moves, the hammer moves with the pile. So that after striking, the hammer does not rebound off the pile. Okay. So do you understand this thing or not? This last statement is giving you this law. That was the code and we decoded it. Before moving forward, is everything clear so far or not? Okay, good. Is there anyone who thinks that anything not clear? Because we have not yet started solving the problem. We are just understanding the problem statement right now. Okay, so let's start solving the problem. Okay, so the first thing is that we don't know what is the velocity of the hammer when it is about to strike the pile. We don't know. Okay, so we're going to use the chapter number 14 technique to find out what is the velocity of the hammer just before striking the pile. Okay, so for that, what we can do is that we can apply the principle of work and energy, okay, and we can apply this. This is basically the potential. Uh, okay, so we are applying it over the hammer. Okay, so let's say that initial point where let's say this is point 1, sorry, this is point 0, and this is point 1. Point 1 is just before collision. So this is the point when the hammer is almost in contact with the pile, but it did not come in contact, just very close. Okay, just wait 2 minutes for the azan to finish, and then we're going to start back. Okay, so now let's see the solution. Yes, one of the student is asking a question and another student answered it correctly. Yes. Okay, so so what we do is that we say, okay, this is chapter number 14, part 2, where we talk about the potential energy. Okay, so here there is no spring, so we have the kinetic and potential energy. So initially, the hammer is at rest, so VH will be 0 initially. And let's say here we have decided that the datum we placed at the top of the pile. Okay, so we will have the potential here. Okay, WH into Y naught. We will have the potential here. And then finally, we need to know what will be the velocity of the hammer. But remember, this is just before striking the pile. I mean, it has reached the pile, but at that time, we paused. Okay, we make the time to stop, and now we are doing the calculation. So this is just before striking the hammer, just before striking the pile. It has reached the pile, but not yet strike it. Okay, so this is VH. So that will be the final velocity of the hammer, VH1 here. Okay, plus since we are already at the datum at this point, so Y will be 0, so this time will be 0. So here we find out that what will be the velocity of the hammer just before it strike the pile. Okay, before moving forward, do you understand this point or not? Is it clear? Is there anything which is not clear? Please ask. Okay, so now we know what is the velocity of the hammer just before striking. Okay, so now what we can do is that since we need to find out what is the impulse, okay, but for the finding out the impulse, we should know that what after striking, what is the velocity. We know one thing, that after striking, the velocity of the hammer is the same as the velocity of the pile, but we don't know how much it is. So we can find it by applying the conservation of momentum. Okay, by applying the conservation of momentum principle. So how it will be applied? It will be applied like this. So you see here, we have the velocity of the momentum of the hammer plus momentum of the pile equals to momentum of the hammer plus momentum of the pile. This is initial total momentum. This is the final total momentum. Now for the initial total momentum, we know that the pile was initially at rest. But the initial velocity of the hammer, we are not talking about when the hammer was 0.5 meter lifted up. We are saying that when the hammer was just about to strike. Okay, so that is VH1. Okay, this we know already. We already calculated it. Okay, so that becomes the total momentum initially. This will be the same as the total momentum finally. However, for the final total momentum, we know that the velocity of the hammer and velocity of the pile finally will be same. Okay, that's by that was the code that we decoded. Okay, so we get what is the final velocity. Okay, so that will be so after calculating this, v2 is unknown, and so we can find what is the final velocity of the hammer and the pile. Before moving forward, is this step clear or not? Is there anything within this step which is not clear? Please ask. Okay, now we need to find the impulse. Now we need to find the impulse. Since we need to find the impulse, so instead of taking this whole thing as our boundary, we will consider only the hammer as our boundary. Okay, so if we consider just the hammer as our boundary, okay, we apply the boundary over the hammer only. So it's mvh1 plus impulse equals to mvh2. We know velocity 2, we know velocity 1, we know the mass of the hammer. We can find what is the reaction force. So with this, so that's the solution of this problem. The problem itself was a little difficult because the problem statement had a little code and you need to decode it, and decoding was not easy if you don't really have much understanding of the process. You cannot decode it. So but anyways, after decoding, it's not a bad problem. Actually this is a very good problem for the instructors to give in the exams, because here you have chapter number 14 and then chapter number 15, conservation of momentum apply, then chapter number 15 apply only over a single body to find out the reactive force. So many things happening in one question. So anyways, in the solution of the problem, is there anything which is not clear? Please ask. So I hope everything is clear. Okay, let's move over to the next example. We have a 350 megagram tugboat is used to pull the 50 megagram barge P with a rope R. The barge is initially at rest and the tugboat has a velocity of 3 meters per second. When the rope is slack, determine the velocity of the tugboat right after the rope becomes taut and the towing impulse force. So again, for this case, you need to solve the problem 2 times. One time by considering as the conservation of momentum. Okay, so mass into velocity of the tugboat plus mass and into velocity of the boat initially equals to the final overall momentum. Okay, so initially the boat was at rest. Okay, so the tugboat, so initially the barge was at rest. Sorry. Okay, and the tugboat has a velocity 3 meter per second. So we have this momentum plus 0. Finally, obviously, since they are connected with the rope, so finally they both are going to move with the same velocity. So it will be VT2, VT2. Okay, we know the mass of the tugboat, we know the mass of the barge, we can find out what is the final velocity. And once we know the final velocity, the next thing is that we can find out what is the towing impulse force. So if we just consider, let's say, the tugboat, then mvt1 plus force average times multiply by time equals to mvt2. So we can actually find out what is the towing impulse force. So is there anything which is not clear? Because it is exactly the same as the previous problem, only a little difference, because here we are having a tugboat and the barge. There we were having the hammer and the pile. If anybody want to ask anything, please ask. Again, why F negative? Why F negative, where it is? We want to put the answer in positive. The value here is bigger than the value here. So we wanted to put the answer in positive. That's it. Is it clear? Okay, anybody else who want to ask anything? Okay, if everything is clear, then we are already done with chapter number 15, part 1. So that's it for today. If you want to ask anything, you can ask. Otherwise, we can finish our lecture right now. Okay, inshallah, meet you next week. Next week, you have exam, right? Yes, next week you have exam. Okay, inshallah, meet you first in the lecture next week, then for the exam. What is the material for mid 1? Okay, oh yes, I didn't mention that, I think. The material for mid 1 will be chapter number 12 and 13 only. The material for the first midterm will be chapter number 12 and chapter number 13 only. Chapter number 14 will not be included. The reason is that Dr. Salim group is a little late. That's why we have to just, because the exams has to be same and at the same time. So we have to just put chapter number 12 and 13 for the midterm. So when you come for the midterm, please bring your homeworks with you, okay? For chapter number 12 and 13. Okay, that's it for today. Thank you.